Hello, this is Mr. Ferris, and this is a video that's going to introduce you to Chapter 9, which is all about testing a claim. Hypothesis testing, significance tests, they are all the same. So in your textbook, on page 536 to 537, there's a story about body temperature. And as you know, supposedly the average body temperature is 98.6 degrees. You've probably heard that your whole life. But there was a researcher, Alan Shoemaker, that decided to test that claim and see if that's really true. So they gathered 130 randomly chosen 18 to 40-year-olds, and here's the data. When you look at the data, you'll see a couple things. First of all, the 98.6, what it's supposed to be, or what people think it is right about there. But you can tell that the average of this data, it states it down here, the average of this data is more like 98.25. So this is the X bar. This is the sample mean, and it is a little bit lower than 98.6. Additionally, proportion-wise, if 98.6 was actually the correct answer, if that's the true body temperature, then 50% of people should be below and 50% should be above. But they calculated that it was actually 62.3% of people are below 98.6. So both of those statistics would indicate that perhaps body temperature of people is really not an average of 98.6, which would make a difference, because when you have a fever, you know, it makes a difference. Every degree kind of makes a difference. The question, though, is this sample that they chose this one time, is it just randomly off? Or is this significantly lower and we would have evidence that maybe it's a real difference? That's really kind of the question that we're trying to answer with hypothesis tests. Data, as we know, is going to vary. So the question a hypothesis test tries to answer is, okay, the data did vary, but did it vary randomly? Or did it vary because of some cause? So our job now will turn to significance tests. We just finished a chapter on confidence intervals. That's one of the major statistical inference procedures that you can learn. And confidence intervals, though, their job is to estimate some population parameter, estimating the true mean of something, perhaps, or estimating the true proportion of something in the population. That's what we did in Chapter 8 with confidence intervals. Confidence intervals are designed to make estimates, find out how big or how much. But the second type of inference, which is what we're learning right now, is called significance tests. And with significance tests, we do something a little different. We just want to assess the evidence and decide whether we believe the evidence shows a statistically significant difference, like a rare or surprising difference based on probabilities, or is the difference really not that big of a deal and could just be attributed to random chance and therefore really not caused by anything. That's really what significance tests are all about. So to demonstrate that, we're going to think about a free throw shooter that's claiming that they are a 80% free throw shooter. That is the claim. So if we have a free throw shooter that claims that they're an 80% free throw shooter, we can take him down to the gym and say, all right, we're going to give you 25 shots and we'll see if we believe you or not. So let's pretend we have a basketball player in the gym. We're going to simulate that they're shooting 25 free throws. Again, their claim is that they're an 80% free throw shooter. So let's see what happens over time if we let them shoot 25 shots. So out of 25 shots, this is what they got. They got 68%. So the sort of thinking we want to do now is, all right, they claim 80%. We gave them 25 shots to collect some data and evidence, and they end up hitting 17 out of 25, which is only 68%. So now what are we going to decide? Is 68% close enough to 80 to believe that they're still an 80% free throw shooter, or is 68% far enough away that we start to doubt and think that, well, maybe they're only 70 or 75? This is the idea of a significance test. This is what we're trying to do. What we will learn are some of the calculations that will give us the percent chance that this person would have hit 68% if, in fact, they really are up here at 80. And if it's a really low probability that they would be this far away, if they were an 80% shooter, then we'd probably be suspicious and suggest and conclude that they're not the 80% free throw shooter. But if what are they, 12% away? If they're only 12% away from 80, we might think, oh, that's not really that unusual. That could just be a random difference. And so maybe we don't think they're lying. Now, of course, we can click this little button right here and see what the right answer is. So in your mind, I want you to decide whether you think they really are an 80% free throw shooter or whether they're not. And then I'll show you the answer in about 10 seconds. All right, here we go. Turns out they were a 60% free throw shooter, and they were hitting a little bit above their average for this particular trial. All right, let's do a new shooter and see what happens. They're not looking so good. So out of 25 shots, they only hit 36. I think probably most people in the room at this point would say there's no way they're an 80% free throw shooter, and turns out they were a 50% free throw shooter. So if you decided that they were not 80, you are correct. Let's try a new shooter. All right, so they're 52%. I think that's even lower than the 68 earlier, so I'm guessing most of you would suggest that this is probably not an 80% free throw shooter. And in fact, they are a 50% free throw shooter. Let's try a new one here. Maybe one more. This is a 64% statistic. P hat is 64%. The claim is 80% for P, and if we show the true probability, it turns out they were a 55% free throw shooter. So I was hoping to get one that was maybe closer to 80. Let's try one more maybe. We'll try one more new shooter and see what we get. Now, shooting free throws is really not like a machine. Humans are probably going to have a different true probability as they go through life, but we're kind of making some assumptions here. Okay, so you get the idea. We have a claim, we have evidence, we compare the evidence to the claim, and we try to make either a reasonable assumption, or in our case, we're going to actually be able to get some probability calculations in our mind, and we'll be able to quantify our level of concern or surprise, and we will have a pretty good idea of what to decide every single time. So now let's turn to our guide, our Chapter 9 guide, and walk through a few of the problems that relate to the story about body temperature. So first of all, there was some evidence we mentioned that was a claim against the claim that it was 98.6. And what were the two pieces of evidence? Well, the percent below 98.6 should have been 50%, but it was something like 62.3%. Normally, about half of all people will be below the mean, but there was clearly more than half below the mean. So that was some evidence against the claim that it's 98.6. The other claim is that the sample mean was 98.25. That doesn't seem like it's very far from 98.6. Of course, it has to do with the standard deviation. The standard deviation is probably really small with something like this. But the mean was low. The sample mean was lower than the claim, and so that would be evidence that maybe the average temperature is actually lower. Now, this question here is a very important question. There are actually two explanations for why the mean would be below the claim. One possible explanation is that the true average really is less. The true average temperature is, in fact, less than 98.6. So it's possible that we really have, either we've changed or we've just got better data, and maybe the mean really should be 98.25. So that's one explanation. The second explanation is the true average is still 98.6. That could be a possibility. But we just got this answer by chance. Sorry for the writing that's so messy, but it's kind of hard to write with this little tool here. So the other possibility is maybe it really hasn't changed. Maybe it's still 98.6, just like it's been for decades. But maybe we just got a weird sample and it was 98.25 by chance. Those are the two reasonable explanations for why we got what we got. And that's generally always going to be true, and what we're going to try to find out is how can we apply probability to figure out the likelihood that we would have gotten something by chance. And then we might be able to eliminate that as a possibility and then claim that, okay, it really must have gone down then. So here's another story. There was a study, interesting study in an economic magazine about corporate CEOs. And apparently there was a thought that CEOs born in June and July are fairly rare. You would think that every month you'd have about a 12th of any sort of group of people. But for some reason, they felt like CEOs tended not to be born in June and July. That just seemed like an odd thing. And so they decided to test the claim. And they took a survey, and they found that out of 375 CEOs, only 45 of them, which is 12%, only 45 of them were born in June and July. Now, if they were fairly represented, then it should be 2/12. 2 months out of 12 people would be born in June and July. But it turns out that instead of, what's 2/12? 16.7%, I believe. So instead of getting something more like 16.7%, they got 12%. That's a 4.7% difference. Is that significant? Is that really a big deal, or is it not really a big deal? Well, it turns out, again, the two explanations are the same, two possible explanations. This difference could be real, or it could be random. And our job, and the thing that we're going to learn how to do, is figure out whether we have evidence that it's just a random difference, no big deal, or is that difference unusual and not likely to be due to chance? Therefore, is this a real difference? Of course, the question then would be, if there's a real difference, well, what's causing that? That would be a whole nother question. That's not under the purview of statisticians. That would be under, I guess, social scientists or something. So how do we decide which of the two explanations are more likely? Well, there's lots of ways. We could actually do a simulation. We could simulate grabbing 375 CEOs over time and see what that looks like. So here's a simulation. We're simulating grabbing 375 CEOs under the assumption that there's a 2/12 chance of June and July. And it turns out that the probability of getting people that are getting 12% or less CEOs that are born in June and July, look at the probability of that happening. Less than 1% chance. There's a less than 1% chance that you would get results this extreme or even more extreme if there was really equal representation. So this would start to suggest that getting 12% is a pretty rare event indeed, if in fact CEOs are equally represented. So we would have evidence that looks like that maybe CEOs are not actually represented equally in June and July. Another possibility is to think about a sampling distribution. Think about a sampling distribution that would represent this scenario. So you can imagine from chapter 7, if we had a sampling distribution, if the true value was 0.166 repeating, and we get 12%, we could figure out the probability of getting something this extreme, 12%, or even worse. And it turns out, I've done the calculations, it turns out to be, again, less than 1% chance, 0.007% chance of getting something this extreme. And then, of course, after just doing chapter 8 confidence intervals, we could build a confidence interval. If you do a 95% confidence interval for the true, based on our sample, you get from 8.7% to 15.3%. So again, that's based on our p-hat of 12%. And if you build a confidence interval, we would be very confident that the true difference is somewhere between 8% or the true percent should be somewhere between 8% and 15%. So based on our sample of 12%, the trues should be somewhere between 9 and 15. Well, the claim, was 16.7. So since 16.7 is not in that interval, we would have evidence from our sample that the true percentage of CEOs born in June and July is actually not 16.7. The entire interval is below 16.7. So once again, we would have evidence that it's actually less than a 2/12 or fair representation. All right, if we move on to page 70 in your guide, we get to some of the actual steps that you do when you are doing a hypothesis test. So in science, I think you've probably done some hypothesis writing maybe when you're doing experiments. In statistics, we always write two hypotheses. We write what's called a null hypothesis, it's spelled N-U-L-L. A null hypothesis is sort of a hypothesis that states the status quo. It states what's going on if nothing is really changed or different or weird or abnormal. Some people say that kind of the null is dull. It's just kind of a way to remember that it's really not the exciting thing, it's just the thing that's always been going on. Or maybe it's that there's no difference, there's no change. I like the term status quo. So in the CEO example, the null hypothesis would be that the true proportion of CEOs born in June and July is 16.7%. That would be the null hypothesis. There's no change, there's no difference, there's nothing going on. It would be what you would expect, 2 out of 12 or about 16.7%. That would be the null hypothesis. Now the alternative hypothesis is usually the thing that you're either suspicious of or some sort of a claim that we hope maybe, if it's like maybe a new drug that's going to help cancer patients, we hope, or we suspect maybe is true. It's the thing that we're actually testing. So with the CEO story, the thing that we were suspicious of based on our sample, we're suspicious that the true proportion is actually less than 12%. It seems like there's less less than 16.7%. So there was a suspicion that they are underrepresented. That word was in the story, I believe. They're underrepresented, and so that's why we're writing that as less than. So if there's really nothing going on, if it's status quo, if there's no difference, then it's 2 out of 12. It's the fair representation. But if there's something going on, then it's less than 16. And only one of these two is going to be supported with data. So that's how you write null hypotheses. Now, the one thing we always want to do as a habit is define P. P is the parameter of interest. So we want to make sure we define this. So P is the true percent of CEOs born in June and July. We always want to define our variable when we are writing hypotheses. It's always going to be the parameter of interest, because remember, that's the thing we don't know. We do not know what the true is. All we know is that p hat is 12%. We have a sample proportion that we know. What we don't know is what the true parameter is. So our hypotheses will always be about the thing we don't know, which is the parameter of interest. So for this problem, it would be that the true proportion of CEOs born in June and July is 0.16 repeating. All right, there's a difference between a one-sided test and a two-sided test. The problem that we just wrote down is a one-sided test. One-sided refers to the alternative hypothesis symbol. And when we did our little diagram here, you might have seen that because we were testing on whether it's less than 12%, this is considered a one-sided or a one-tailed test because we're only concerned about if things are less. If things are greater, that's not a big deal. But we are concerned about underrepresentation of CEOs, so we're concerned about less than, so less than ends up being a one-tailed or a one-sided test. Now, you can imagine there are situations where perhaps we might be interested in either side. Like maybe there's some bolt that's supposed to be used on the space shuttle, and of course if it's too big it won't fit. If it's too small it won't fit. So being both too big and too small would be bad, and we're trying to make sure bolts are always within, you know, a certain tolerance of the right mean width. So basically a one-sided test will always be using either greater than or less than. And so some of the words you might see are larger than, or greater than, or has it increased. You'll see words in your directions in the stem of the problem that indicate, well, that would be for the first symbol, of course, or you might see smaller or gone down. There will be words that will make the direction very, very clear as to whether it's going to be something going up or something going down. A two-sided test, in the alternative hypothesis, you'll just say not equal to. So words like that, they might just say, well, is there a difference? Has there been a change? Both of those words don't really indicate a direction, like gone up or gone down. So if they're just testing a difference or testing a change, then that would be a two-sided test. And in those kinds of cases then, if you think about kind of the normal model that we'd be under, if the claim is here and you're trying to find out if it's changed, you would be worried if you landed too far outside here, and you'd be worried if you landed too far outside here. So anything that lands in kind of the extreme areas on either side would be suspicious, but it would have to be, of course, pretty far out. So there you go. That's kind of the first foray into significance tests. You now have an assignment coming up just to do a little practice. So I will stop this video and let you do some practice.